we're going to start by just revising a little bit Rutherford's model. So hopefully what you guys remember from Rutherford's model is that Rutherford discovered that most of the mass of the atom and all of the positive charge is concentrated in the nucleus. But Rutherford knew there were electrons inside the atom as well, and so his solution to what to do with the electrons was to use the electric attraction between the negative electrons and the positive nucleus and have those electrons orbiting around the nucleus, kind of like planets around a sun held in orbit by the electric force. However, there's two major problems with this model that we need to know about. The first one is that to cause electromagnetic radiation, we accelerate charges. Like if we want to broadcast radio, what we do is accelerate the electrons in the radio transmitting device up and down inside the area. And so if these electrons really are going in circular motion about the nucleus, that means they're experiencing centripetal acceleration. If they're experiencing acceleration, then they should be emitting energy, and that means that their orbits will decay and they will crash into the nucleus, so the atom would be unstable. The second problem is that whatever model we have of the atom, it has to be able to explain the light that's emitted by the atom when we pass electricity through it, and so the atomic line spectra. And there's nothing in this model of Rutherford's that explains like the characteristic colours of light that are emitted by hydrogen gas, for instance, or any different element. Every element emits a unique set of photons which have unique colours, unique energies, and this model doesn't explain that. So the problems that we have to address. So that's kind of like the background to it. And so we're in the same time, this is just a couple of years after Rutherford proposed his model for the atom. There was this other guy called Niels Bohr, B-O-H-R, came along and he proposed a model. He combined the atomic line spectra of hydrogen with Rutherford's newly minted idea of a nucleus, and he proposed a model just for the hydrogen atom. His model doesn't work for any other element, but it does work for the hydrogen atom. Bohr stuck with the nucleus at the core of the atom, but the key difference between Bohr's model and Rutherford's model is that instead of having electrons orbiting around the nucleus, or in hydrogen's case, right, an electron. Hydrogen's only got one electron. That's why we can do hydrogen. It's simple. It's only got one electron. So we don't have to worry about electrons interacting with each other. We just worry about one electron. And so Bohr's solution was that instead of having the electron orbiting the nucleus, the electron has a series of different energy levels that it can inhabit. And Bohr allowed the electron to move back and forth between energy levels by emitting or absorbing photons. And so a photon is energy. If the electron wants to move up an energy level, it needs to absorb a photon, and if it wants to fall down an energy level, it needs to emit a photon. And the reason why those photons have characteristic colours is that the energy differences between those energy levels were constant. So for any hydrogen atom anywhere, the difference between the energy levels is the same amount. Same amount of energy, same colour light, and that explains why we can see the characteristic colours of light from any element, including hydrogen. So if we're trying to visualise what this looks like, it's a series of ever closer and closer and closer energy levels about the nucleus of the atom. And we're going to give them numbers, right? We're going to start from the middle and work out. We're going to call this one number 1, number 2, number 3, number 4, number 5. And so the way that Bohr's model explains the atomic line spectrum, what Bohr said is that whenever an electron falls down from energy level number 5 down to energy level number 2, that's when we see a visible photon of light. So if it falls from 5 down to 2, if our electron does that, we see a purple photon. If the electron falls from number 4 down to number 2, we see, what colour photon do we see? Blue, right? From 4 to 2. So the S number and the L number are suddenly starting to take on a physical meaning. And which two energy levels does it transition between if it emits a red photon? 3 and 2. So if it falls from 3 to 2, we get a red photon. And so any electron transition downwards that ends on the second energy level is part of the Balmer series, visible light. If it falls down from any energy level down to energy level number 1, we call that the Lyman series, and so on. So suddenly these series, these names of series, take on meaning. They tell us the energy level that the electron ends up in. The S number, the series number, is the energy level it falls down to, and the L number is the energy level it starts off in. And so what we're saying is that, first of all, electrons inhabit energy levels of fixed, quantized value. So when something's quantized, it means we give it a fixed value, and it can't be anything else. And so each of these energy levels has an energy value associated with it, and there can't be anything in between. Now, you can either be at energy level number 1, or you can be at number 2. There's no 1.5. You can either be at 1 or 2, and it's that quantization, that giving them fixed, discrete values, that means we get those very particular wavelengths of light, energies of light, that are emitted. So electrons can transition between energy levels by absorbing or emitting photons. If the electron absorbs a photon, is it going to go up or down energy levels? Up to a higher number, right? So absorbing is up and emitting is down. And the photon energy is equal to the energy difference between the energy levels. And so the only photons that are going to be absorbed are ones that are exactly equal to the energy difference between the energy levels. So if we shine light through hydrogen gas, the only photons of light that will be absorbed are going to be the ones that exactly have an energy that matches the energy difference between some energy level on the hydrogen atom. If it doesn't match, that light's just going to pass through. It can't be absorbed. And the same with emitting. So the colour of light emitted is going to be exactly equal to the difference between the energy levels.